doing the talks, and I won't introduce Nick now because I did yesterday, but today he's going to talk on geological journeys of discovery, the wow factor in South African geology. So if you can speak. I know, don't worry, I've got it.
Charlie? Oh, you switched it up. Good, thank you. Thanks, John, for introducing me yesterday. And thanks are due to Charlie, who is the technical assistant here, or he's the manager of technical things, and he sets it all up as it is and does the sound, and this whole talk would be half of what it's going to be without Charlie. Charlie. Thank you. That's for you, Charlie. That's for you. Will there be violent objections if I switch the lights off? No. Goody. We drive along the highways, we drive through ports, we drive over passes, we see amazing geology, and we now have some books to help us have some idea of what we are seeing. But those are not the only journeys of discovery that we make, geological journeys that we make. There are all sorts of other discoveries, and I had occasion the other day to look up the word epiphany. And in the Christian calendar, the first Sunday in the year is Epiphany Sunday. And I thought, well, that's interesting. We use the term, I don't, but you see it used from time to time. This person or that person had an epiphany, and I've always had a vague idea of what it meant. So I did what one does, which is to Google it, and the definition I found on the internet for an epiphany is the experience of a sudden and striking realization. And what we'll see this afternoon may not be sudden, but it'll certainly be striking. And I think it's just, these are some of my own personal epiphanies. And I'm going to divide the talk into three parts. The first part will probably be the longest. And before I do that, I'm going to explain why, in a talk on South Africa, I have a map of the Pacific Ocean, or a map of the world, with unusually, we usually find Africa in the middle of such a map, but this one has the Pacific Ocean in the middle. And there's a reason for that, which I'll come to in a moment, but more about the Pacific. Probably most of you in this room know that around the entire Pacific, with the exception, as far as we know, of Antarctica, is the so-called Ring of Fire. It's a belt of very high incidences of both earthquakes and volcanoes. I've lived for some years in Chile, and I can assure you that regularly in Chile you experience earthquakes. You fly over in light planes or helicopters valleys where the course of a stream has been completely blocked, dammed by a lava flow. The lava flows, in some cases, are still glowing at their ends. So I've experienced some of that, and we all see in the media from time to time about earthquakes, whether they are in New Zealand or Japan or Argentina. We read about volcanoes, Mount St. Helens, etc. And those are the incidences of earthquakes and volcanoes around the Pacific. So why start a talk on Africa in the Pacific? If one were to drill a hole, supposing such a thing were possible, from somewhere near the middle of the Pacific through the center of the Earth, I guess it would probably come out somewhere near the middle of Africa. And that is the reason for starting the Pacific. The Pacific is extraordinary. It's huge. It's by far the biggest ocean we have. And it's surrounded by a very geological phenomenon, the Ring of Fire. So why mention the Pacific in a talk about Africa? Because if one were to reconstruct the continents as we know them today in geologically past versions of plate arrangement, Africa would usually be at the middle, and what has happened, at least in the last couple of plate tectonic breakups, is that other continents have moved away from Africa. They have moved, by and large, into the Pacific, which is why we have this Ring of Fire. There is no such thing in Africa. We do have volcanoes, we do have earthquakes, and they are to do with rifting rather than subduction, which is what's happening around the Pacific. And I'm sure you all have made yourselves familiar with some of the plate tectonic terms, and subduction would be one of them. But we have a continent that is drastically different to all others. And I'm going to fly a kite here, and I may be shot down by the geologists in the room and any other geologists who hear about what I've been saying. And I'm going to suggest that one of the reasons why Africa is so special is that it has a unique relationship with the deep mantle below it. In other words, if one looks at continents that have drifted away from Africa, they have drifted over the mantle. Africa has stayed where it was, its roots tucked deep into the mantle. And that relationship of the crustal part of Africa with the mantle deep below has given Africa, particularly South Africa, an extraordinary legacy. And those are some of the things. Well, I'm going to talk about some of those parts of that legacy in the next few minutes. I'm going to talk about some mineral deposits, not specific mineral deposits, but in the broadest possible terms. I'm going to talk about some rocks that have been named in South Africa. And because these things don't just happen, people make discoveries. I'm going to talk about some of the people who have been most instrumental in bringing these absolutely amazing phenomena to light. So we'll be learning a bit about minerals, we'll be learning about rock names, and we'll be learning about a few of the people. Right. One of the aspects of the relationship of the continental crust with the mantle is the so-called cratons, which are the ancient parts of the continents, which have been metamorphosed, folded, a lot changed, but essentially have been around for 3.5 billion years at least. And that map shows you the African cratons. It also shows you the incidences of gold and diamonds. In another map, on another map in the same paper, you would see that between those cratons are fold belts, belts of folded rocks, where other minerals are restricted. Other minerals don't occur, like copper, for example, don't occur much on the cratons. They occur mostly in the belts, the mobile belts, the fold belts, between the cratons. And it's important for me to make the point at this stage that the relationship of mantle, particularly the cratons, with crust, particularly the cratons with the mantle, is important in our mineral legacy. And I'm going to talk about three minerals, or two metals and one stone. By far the most precious metals are gold and platinum, and by far the most precious stone is diamond. And all of those are part of our extraordinary legacy in South Africa. So let's have a look at gold. I'm sorry, this is not a very useful map. I beg your pardon for even showing it, but it gives you some statistics. Ghana certainly has not produced, or will not, or did not produce in 2018, 7.1% of the world's gold. As you'll see, it's on the far right-hand side of the bottom graph of columns, so that's a mistake. But it gives you an idea of the present production, or the last year's production, expected production of gold around the world. This is a more reliable figure of where the gold has come from, and you will see that in 2011 South Africa was just behind West Africa. In 2017 it's fairly substantially behind West Africa. There you have the main gold producing countries of West Africa coming up with 390 metric tons of gold metal, and South Africa 140. But don't be deluded by that. In the last nearly 150 years, South Africa, in fact not South Africa, the Witwatersrand Basin has produced a quarter of the total production of gold. That's one little basin in a small part of what was the Transvaal. Let's say, and I have made no attempt to do a statistical estimation of this, but let's say the area of the Witwatersrand is 0.1% of the area of the surface of the continental globe. So 0.1% of area, the Witwatersrand Basin, to have produced 25% of the world's gold is freakish, absolutely freakish. And one has to say, what is the reason for that? How has that come about? And I submit, and this is where I stand exposed to be shot down by my geological colleagues, that it's something to do with our special relationship with the mantle deep below. There it is, the Witwatersrand, just over 300 kilometers by about 150, 200. Not very big. It's a single basin divided into sub-basins, and right there in the middle, almost like a bullseye, you see the Vredefort Dome. And it has sustained dozens and dozens of mines over its 150 years of existence. It has produced this absolutely bizarre amount of gold, and it is just something which, in my mind, is definitely worth a wow. It's the first instance of gold having been found in reefs which were not the old kind of reefs, which were in fact usually quartz veins or shear zones or narrow cross-cutting features in rocks. When they discovered the first hard rock gold in the Witwatersrand, they found, to their amazement, that the gold persisted over a very narrow width, usually, a meter in any particular reef or less than that, for hundreds of meters, if not tens of kilometers. So here were these extraordinary reefs, completely unlike any reefs that had ever been known before. And that's what they look like. The speckled pinkish or reddish bits between the yellow and green and other colors are the gold reefs. There are lots of them, and they go on and on and on and on, which is why we have gold mined in Kinross, Evander, we have gold mined right across the central Witwatersrand, and we have gold mined in Welkom. So it is indeed a huge area, and you have to ask how all that gold got there. Now, that's a picture of some drill core with beautifully rounded clasts, which is what we call any fragment that has been, any element of detritus that has been washed into a sedimentary phenomenon, whether it be a stream or a beach or whatever. We call them clasts, and those clasts are beautifully round. Those clasts are of iron pyrites, or pyrite as geologists call them. And the important thing about the pyrite is that the Witwatersrand mostly has gold associated or held in pyrite, which is important, as we'll come to see. There are the unique thing about the Witwatersrand, apart from its content of gold, is its age. Until quite recently, it was considered as Proterozoic, which is not the oldest age formation we have on Earth. That is the Archaean. The Archaean used to be considered as all what we call greenstone belts, such as we have around Barberton, and scattered around the old Transvaal and northern Transvaal, Zimbabwe, over huge areas of Canada, in Australia, etc. They were considered to be Archaean, and everything formed on top of them was Proterozoic. Now, the Witwatersrand is considered to be Archaean. There are other Archaean gold deposits where the gold is held between pebbles in a conglomerate. There's one in Brazil called Jacobina, and there's one in Canada, which is mainly uranium producing and not gold producing, which is called Elliott Lake. And the other two, the Brazilian and Canadian ones, are quite a lot younger than the Witwatersrand, and they all have pyrite, but none as richly so as the Witwatersrand. Those are smaller grains of pyrite in, not typical by any means, but in a Witwatersrand reef. It's almost solid pyrite. To give an illustration of how extraordinary the Witwatersrand is, I've chosen to compare it with a basin in northern South America. It extends over a large part, or not a large part, because Brazil is a huge country, but a part of Brazil. It extends over a lot of Guyana and quite a lot of Venezuela. It's called the Roraima Basin, and it has wonderful conglomerates. I worked there in 2004. We did a drilling program exploring the conglomerates. It's a large basin. It's approximately the size of the Witwatersrand. It has conglomerates. It's old. It's not Archaean, but it's old. We drilled thousands of meters of exploratory boreholes, and we found not a single exciting intersection. So that is what can happen. Basins like the Witwatersrand, sedimentary basins, occur there are probably hundreds of them around the world, bigger and smaller than the Wits Basin, but the Roraima Basin in South America is one of those. It has, as far as one can see, other than not in conglomerate setting, it has no gold to speak of, although they dredge large amounts of gold out of the rivers, and the source of that gold remains a mystery. But an important factor is, A, the reefs, the conglomerates, are much younger, and B, they are not pyritic. So it does draw attention to the age of the Witwatersrand and the fact that in those days, long before the atmosphere was predominantly oxygen-rich, you could get sulfide of iron, you could get sulfide of uranium being washed into the rivers. Today, it wouldn't happen. It would all be oxidized. But in those days, the atmosphere was very, very different. The change of the atmosphere came about by the, as much as anything, by the photosynthetic role played by fossil, not even fossil, there are still stromatolites. You might have heard of stromatolites. Stromatolites are wonderful reef-like marine creatures which exchange the CO2 in the atmosphere for oxygen, which they pump back. So 2 billion years ago, the atmosphere started to become significantly more oxygen-rich than it was in the days of the Witwatersrand, when pyrite and highly soluble uranium were being washed into rivers and onto beaches. There is a picture of a Guyanese conglomerate. It looks like any conglomerate you might see in Johannesburg, but it's devoid of gold. This is a remark that I was very happy to see, because there has been a debate for the entire length of time that the Witwatersrand has been known as to whether the gold came in with the pebbles which form the reefs, or whether the gold came in later, brought in by solutions from deep below, and the jury is still out. There is no resolution to that dilemma, the debate. And again, at the risk of being shot down by my peers, I would like to go with the middle of the road answer, which is that the pyrite and certainly the pebbles and a lot of the material in the conglomerates was primary detrital. It came in with the streams. The gold, most of it, some of it probably came from the greenstone belt surrounding the basin. The gold, I would like to think, came from below. I have heard an argument that says there is no way in the world that the amount of gold in the Witwatersrand could have come out of the surrounding countryside in streams. It had to have come from below. And if you accept anything like that argument, again, it turns one's eyes to the deep-rooted cratonic parts of our crust and the mantle below. This is an observation or a comment by McCarthy and Rubich in their wonderful book, The Story of Earth and Life, and they are prepared to leave it unresolved. I don't know if any of you saw South Pacific, but there's a lovely song in that, Some Enchanted Evening. And one of the lines in that song goes, "Who can explain it? Who can tell you why? Fools give you reasons, wise men never try." And basically that's saying the same thing as Spike McCarthy and Bruce Rubich said. So there is the extraordinary wow factor phenomenon, which is the Witwatersrand Basin with its gold. Now we move on to diamonds and kimberlite. There is a story, I'm not sure if it's apocryphal or not, but it's such a good story that I'll tell it. about some diggers in 1871. The first diamonds were discovered the first diamond in the singular was discovered on the farm de Kalk. We saw gravels there, gravels on that farm in one of the slides yesterday. And others were found on the Orange. That was on the farm de Kalk, was on the Orange. They explored the Orange until they got to the Vaal. They went up the Vaal, and the Vaal, in fact, was more productive. So there were diggers along the Vaal and the Orange, and they were coming in from all parts. They were coming in from Durban mostly, a lot, it was closer, and a lot from Cape Town. And the story has it that some diggers were on their way to the diamond fields on the rivers, and night was falling, and they saw a homestead ahead with some flickering lamp lights from inside. They needed a place to put their wagons, and they went ahead to the house, and the farmer said, come in, have a meal. South African hospitality has always been famous on the farms. And the diggers, the small party of diggers, went into the farmhouse and shared the farmer's meal. And as they were eating by lamplight, one of the diggers thought he saw a glint in the mud darga on the wall of the room. And he excused himself, got up from the table, went and had a look, and sure enough, there in the darga of the room that they were eating in was a tiny diamond. And he commented on this to the farmer and said, where did you get the mud that you plastered this wall with? And the farmer said, there's a pan a few hundred meters north of the house. We can go and have a look tomorrow. They went and had a look the next day, and they asked the farmer if they could dig a hole. They dug a hole. They dug quite a big hole. They screened it and panned it, and after some time, they found one or two more diamonds. They dug deeper, and they continued to find diamonds. They were soon joined by other diggers, and the next thing you know, there was a whole lot of digging going on near the farmhouse. And what was extraordinary was, A, that the clay that they were digging was nothing like the gravels that they had been finding diamonds in along the Vaal and Orange rivers, and B, that it just kept going. And they dug deeper and deeper, and the clay went from yellow to brown, from brown to grey, got harder and harder, from grey to blue-grey, by which time it was so hard that they had to blast it with explosives, but the diamonds didn't stop coming. Now, their experience until then on the rivers had been that they could dig through gravels for a meter or 10 meters. They would move lots of boulders, pebbles, cobbles, and particularly when they got near the hard bedrock below the gravels, they would find potholes or riffles, and the diamonds would be concentrated there, but they would be up through the gravels as well. So the phenomenon of digging deeper and deeper and deeper and never getting to a bedrock that was sterile was something completely new to them. And these were known as the dry diggings because there was no river anywhere near there. And it was only a matter of time before more areas, they covered the area where this yellow clay was, and beyond that there was the normal shale or sandstone bedrock. Then another pan or feature was found where they encountered the same thing. And before long there were just hundreds and hundreds and then thousands of diggers digging there. They called the little settlement New Rush for obvious reasons, and then they decided that that was not really an adequate name, and they named it after the so-called New Rush tented camp, after the colonial secretary of state, what are they, not secretary of state, the British colonial secretary, Lord Salisbury. I beg your pardon, Lord Kimberley. I do beg your pardon. So that's the story of the discovery of the Kimberlite. But the geologists who inevitably soon enough appeared on the scene were quite bamboozled by this rock. Throughout the hundreds of years of Indian digging, throughout just over 100 years of Brazilian digging, the mother lode of the river diamonds had never been found. Now it appeared to have been found. And what was this rock? It had unusual minerals that they were not used to seeing in volcanic rocks, and yet it appeared to all intents and purposes to be a volcanic rock. And so that's what they settled on, and they called it Kimberlite, and we will come back to that in a moment. But it was important as technology developed and more of these wonderful chimney-shaped or carrot-shaped pipes, Kimberlite pipes, were found. It was important to be able to understand why there was this completely different rock, a new rock type. Where it had come from, what was its origin? And they persisted in their quest. There was a major breakthrough made when they found in one of the Kimberlites, and then others, they found what we call xenoliths, which are foreign inclusions in the Kimberlite, which were extremely heavy, and when enough had been found, some of them were found to have diamonds in them. And their mineralogy was such I'm sorry, I've shot ahead of myself a bit, but I'll come back to that. That's what they look like. But we now know that that's what they look like, but in those days, you can imagine they had very little to go on, and the xenoliths of the very, very heavy material were something that gave them huge cause for thought. What were these xenoliths? That's what they look like. Those are xenoliths from the university here, from the mantle room in the geology department. And you can see a pen there. There's a pen for scale. Any of those would be about as much as one person could carry. They are extremely heavy. And it was soon realized that these were xenoliths from the mantle. They had been picked up by the Kimberlites, so the conclusion was inevitable that the Kimberlites came from below that layer of mantle where these were picked up and were entrained in the Kimberlite as it rose to the surface. From the texture, and that's a mantle xenolith with diamonds, several diamonds in it, and you know that's an extraordinary concentration of diamonds. You wouldn't expect, there's a third one on the left which you can probably see. You wouldn't expect to find 3 diamonds in a piece of rock not much bigger than your fist. In kimberlites, and we need to say something about the grade of kimberlites, diamond miners talk about a grade in carats per 100 tons. A carat is 0.2 of a gram. And so for 0.2, I worked it out, but for 0.2 of a gram in 100 tons is 100 million grams. Is it? It's a phenomenally low grade in any event. I'm sorry, I haven't done the maths recently, but it's a phenomenally low grade. In other words, if you see those pictures of trucks coming out of any big diamond mine or any mine, a lot of those trucks carry somewhere between 50 and 100 tons. Sometimes they carry more than 100 tons. So if you're looking at an economic grade of kimberlite, you can make money with, provided your diamonds are good, you can make money with 12 or 15 carats per 100 tons. So in the Letseng mine in Lesotho, where because the stones are huge from time to time, 600 carats, they can mine a grade of 2.5 to 3 carats per 100 tons. In other words, those 100-ton trucks coming out of the mine may be, with luck, carrying one diamond of 2.5 carats. It gives you some idea of how difficult the diamond explorer and miner's job is and why diamonds are expensive. So to find diamonds clustered like that in the mantle zenolith tells you that that's where your diamonds are coming from. The kimberlite picks up chunks of mantle on its way up, releases it's very aggressive chemically towards the mantle rocks, which is why they get rounded on their ascent, and it releases the diamonds into the kimberlite. But the diamonds were not formed in the kimberlite, they were formed in the mantle and released into the kimberlite. What was I going to say now? But the problem when you have such low grades of diamonds and you are doing exploration for them is that you really haven't a snowball's chance in hell of finding diamonds in your exploration. So what are you going to look for? You're going to look for the much more common minerals that occur with the diamonds. And the common minerals, infinitely more common than the diamonds themselves. There's, oopsie, help. Yeah, there's the solitary diamond. All of the red and orange are garnets. The black are ilmenites. The green are olivine and some chrome dioxide. And they are what diamond explorers look for. But not long after they'd found the first pipes at Kimberley, they started finding pipes that had no diamonds. So the challenge was, when you have found a kimberlite, and before you start to sample it, which can involve the taking of hundreds of tons of sample for you to find your diamonds, is there any way that you can tell whether the pipe that you're looking at is probably going to be diamondiferous, maybe diamondiferous, or is definitely not going to be diamondiferous? And that's, we'll go back to, that is the Russian script for Clifford's rule. And the reason I mention Clifford's rule at this point is that the man who conceived that map in 1970 was Tom Clifford. And it was he who gave the diamond explorers a massive breakthrough, which is that if you've got kimberlites that are not punched up through the cratons, don't even bother looking at them. They won't have diamonds. All the diamonds are in the pipes, and kimberlite pipes come up over wide areas which are not on the cratons. They come up along here, along there, around here, and De Beers and others have spent years exploring those kimberlites until Clifford came up with his principle that unless your kimberlite pipe has come up through the craton, it's not going to carry diamonds. So that was a big breakthrough. Another breakthrough came quite a lot decades after that, which was that there is a composition of garnet which relates to diamond-bearing kimberlite without fail. And the composition is called subcalcic. It's low in calcium, it's high in chrome, and it also imparts a particular color to the garnets. And the garnets that diamond explorers look for are these purple ones, and even some of the orange ones. But the red, the deep, rich, ruby red garnets, find them in a sample, and you won't get terribly excited. But find something that looks like that, and you will jump around. You are getting close to where you want to be. So that was the breakthrough that was made by UCT and Mineral Service Group geologist John Gurney, and it was soon being used around the world by diamond explorers. They were using Gurney's rule of the importance of garnets that were subcalcic and high in chrome. And in the meantime, people like John Gurney and others were working on what do the mantle xenoliths tell us? What are we learning about the origin of the kimberlite pipes and the origin of the diamonds themselves that will help us explore for more? And they started putting together a picture of where the kimberlites were coming from. And I'm going to show you a series of pictures. And it's important that I make this comment about mineral services because that's what the mantle and crust look like under the cratons. That's a typical section through a craton and the countryside surrounding it. There is your diamond stability field below the dashed red line. Above the line, the temperatures are too low, the pressures are too low, or there is a critical combination of temperature and pressure at which diamonds will form. So they're forming in the peridotite. Up comes the kimberlite, picks up diamonds in the peridotite. Those are what the diamond specialists call P-type diamonds, and they are thus called, obviously, because they form in the peridotite. But there are others. Here comes a subduction zone. Subducting oceanic crust beneath and some mantle beneath the craton. And that purple layer is a layer of ultramafic rock called eclogite, and up come the diamonds through the eclogite. So not surprisingly, they are called E-type diamonds. Now, how do they get to the surface? Here comes the kimberlite. Kimberlite travels, they used to say, at supersonic speed. By the time it gets to the surface, it starts slowly, but as the pressure gets less and less and less as it approaches the surface, it's starting to move very fast. And they know that because diamonds will resorb completely. They will basically evaporate if they're given enough time. So you've got to bring them to the surface very quickly for them not to disappear. And that's why it is known that these very high speeds of ascent of the kimberlite pipe have to be the case. They form in the peridotite, not in the red part of the asthenosphere, below the peridotite. So that one on the extreme left has come up. It's gone through the diamond stability field, but it hasn't gone through the peridotite at a point in the stability field. So, yeah, that's the story of how diamonds get to the surface, which took decades to work out, and it was thanks to people like John. All right, so we've heard a lot of technical stuff about how the kimberlites form and so on and so on, but where is the wow factor in any of that? Well, I think it is shown in these two tables. Can you read that? Can you read those? Ironically, the top of the list, the biggest diamond of all, was a carbonado diamond found in Brazil just before the Cullinan diamond was found. But the important ones to take note of here are the Cullinan, the next. That one, where is the first? I can't see very well from where I am. Is that the first non-African one? That's the first non-African one. I think there's another one at the bottom, and there are a few on that slide as well. But as you see, 80%, more than 80% of big diamonds, what is the smallest one there is 490 carats. That's a huge diamond. All the big diamonds, 80% of the big diamonds, have come from Africa. And why is that? Why have we been so blessed with our diamond endowment or legacy that we have been able to produce these consistently big diamonds? The biggest one after the Cullinan was found in 2015. It's been recently found. So they're still being found. So it's not as though the Cullinan would never be found again. It hasn't. But at 1,000 carats, 1,100 carats, you're getting to quite a respectable size. And that's a huge diamond. And as I say, 80% of them have come out of Africa, and I submit that it's because of Africa's special relationship with the mantle. I do need to say that even though the kimberlite mines in Botswana and historically in South Africa have produced phenomenal amounts of diamonds, roughly 200 million carats of gem diamonds have come out of Namaqualand and Namibia, the CDM or Monument mines. This is a picture of Hans Marinsky on the right and Jack Carstens on the left. Jack Carstens was the man who in the mid-1920s found a few diamonds near Port Nolloth. And Marinsky got to hear of it soon after, and in 1927, Marinsky got himself to Namaqualand and quite soon had tied up most of the concessions or the claims in Namaqualand. How was he able to do that? Because he knew something that nobody else in those diggings, and you can imagine the frenetic fever that was going on in Namaqualand as people prospected for diamonds. Quite a few diamonds had been found, some very rich concentrations of diamonds had been found, and they didn't know what was the concentrating element. But Marinsky knew. And what he had seen in Namibia when he was, or German West Africa, when he was sent there by the South African government, was that the richest terraces, now you must remember that the diamonds along the coast, along the west coast, occur in terraces which were formed when the sea level was much higher than it is now. There were beaches tens of meters above modern sea level. And there are different levels of beaches. And the one that Marinsky found by far the most diamonds in just south of Ludritz, where he was sent by the government, was associated with oyster shells. These are oyster shells. These are the boulders, and that's an anomalously rich concentration of oyster shells. But wherever he found this terrace, with its rich diamond concentrations, he found oyster shells. So when he went to Namaqualand 15 years later, all he did was look for oyster shells, and he found them. Wherever he found oyster shells, he pegged claims. He pegged claims. He carried on pegging claims. And that was how he was able to tie up the lion's share of the diamondiferous ground in Namaqualand. He didn't hang on to it for very long. Marinsky was getting old. He'd worked hard. He was looking forward to retirement. He'd seen a farm in the Eastern Transvaal that he wanted to buy, and he had a pretty good idea that Ernest Oppenheimer would be interested in acquiring his rights. So that's exactly what happened. Marinsky sold his rights on to Ernest Oppenheimer, and not much later had bought his farm in just north of, or west of Tzaneen, Duivelskloof. Farm is called Westphalia, and he had gone farming. And he was a very successful farmer. I think probably today most of the avos that you eat in South Africa come from Westphalia, and that was a later development. He started farming with gum trees, eucalypts, and he was a very successful farmer. But by the time Marinsky came to, there they are, and that's north of the river. That's an arrangement, and you can see the size of those dunes, and they had to get through those dunes to get to the gravels at the base of the dunes. That was a huge earth-moving operation. This is in Namaqualand, where you don't have the dunes. And you can see the bedrock, the pitted, riffled bedrock, lovely for collecting diamonds. And it was only a matter of time before De Beers went offshore, and there they are recovering them from the seabed, because as much as sea level has been higher, it's also been lower. And there are beaches below sea level, and there are also diamonds being washed out to sea today and throughout time. And it's just feasible to mine those. We've heard about gold and platinum, gold and diamonds, and now we come to platinum. And in 1924, Marinsky was pretty down and out. He was a consulting geologist in Johannesburg, and he received a little bottle in the post with some concentrate in it, and he was told that if he was interested, there was more where this came from. And he was definitely interested, because he was very certain that what was in the bottle was platinum. So he had been told where this had been found. He went out to the farm. It belonged to a man, Maandagshoek it was called, belonged to a man called Andries Lombard. And they prospected, Lombard and two brothers called Skuman, and they prospected for quite a long time without finding much. And then they found this narrow seam or reef of rock, which was completely different to those above and below it. Marinsky knew it was in the Bushveld complex, and he knew enough about the geology, well, enough was known at that stage about the geology of the Bushveld complex for him to know, Marinsky to know, that it consisted of layered, it's a layered intrusive, and it consists of different layers of different composition, and this was quite distinct from layers above and below, and they find it in other spots along, this was near Leidenburg,